Here's another video that's going to discuss Gauss's law. And in this particular video, the reason why it says Gauss's law left-hand side, or LHS, is because we want to focus our attention solely on just this side of Gauss's law for a moment here. The right-hand side and Gauss's law and introduction are covered in other videos. So let's go ahead and take a look at this side here. Gauss's law really needs to be handled with the left side and the right side sort of independently of one another, at least in processing, although the ideas that they represent are sort of related. Let's just take a look then. So what we can do here, let's just go ahead and rewrite this idea so we can stare at it a bit. Our target for Gauss's law, of course, is to be able to solve for E. We'd really like to be able to pull this out of the integral and the dot product and solve for it somehow, because that's going to be what's going to ultimately deliver our answer to us. But as we noted in the other video, we have a dot product in here, and there's a couple things. The dot product definitely needs to disappear. We need to get rid of that. That's the only way to solve for E. And then also we need to be able to handle the integral here without messing E or ds up really at all. And so one thing we can do here is we can always rewrite the dot product as E ds times the cosine of the angle between E and ds. Okay, so as we noted in another video, because of this dot product here is inside the integral, we can't have this angle changing as the integral changes. We'd really like this phi here. We really do not want it to be a function of anything that we're of ds at all. Like, we don't want to have to integrate over a bunch of angle changes because it just makes the integral impossible right here. We really like this angle to be constant somehow. So what that means is when you're processing this left-hand side, is you always have to sort of choose a surface here, choose the so-called Gaussian surface to match your E. And remember that the surface has to be a closed surface right here, because that's what the ring around the integrals means. Now, there aren't that many options for you right here, because really all you have to choose from here are a sphere, a cylinder, or a box. These are sort of the only simple geometries we have that we can get a handle on, at least at the class, sort of at this level here, that are closed. Now, certainly we could come up with some sort of three-dimensional blob like this that went in all directions, but it's impossible even to have some sort of analytical formula for even what is the mathematical formula that describes that shape. So we're going to stick with these simple ones here. And so what you'd like to do then is you really like to be able to pull E outside of the integral right here so you can start to algebraically solve for it. But remember, the only time you can pull something out of an integral is if this is you can somehow expect or make that E will be a constant. Remember, you can only pull constants out in front of an integral. So I think you probably know that, like, for instance, if you're just integrating 2x squared with respect to x, of course you can't pull the x out because you're integrating that, but the 2 can come out of the front. It makes the integral look a little bit easier to do. We'd like to do the same thing with the E. We'd like to be able to pull that E outside of the integral. In fact, always when doing Gauss's law problems, at some point that E will come out front because you've chosen things so that it's constant. So let's look at a case here of maybe a point charge. So I'll draw this two ways, both three-dimensionally and two-dimensionally here. Well, I'll try the three-dimensional, but it's probably not going to work too well. Here's a point charge with a bunch of electric field lines coming out of it. Okay, looks something like that. Now, what Gaussian surface would you choose to put around the point charge here so that, A, it was symmetrical, the surface sort of matched the electric field, and it was something that you could identify a region of this electric field where it was constant, so you could pull the electric field out front of the integral without having to bother with it inside there. I'll go ahead and dispense with a three-dimensional drawing. It's just not going to work, but would you wrap a sphere around this sphere, a sphere around this point charge, a cylinder around the point charge, or a box? Let's go ahead and try the cylinder. If I put a cylinder around this here, I've met the requirement that I'm enclosing some charge because the cylinder is definitely an enclosed object here. I've met the requirement that it's a relatively simple geometrical object here. I know all about cylinders, their radius and height and area and surface and volume, that sort of thing. But the idea that I have not met, I've failed in two cases here, is what on earth am I going to put in for phi here, and have I found a region where the electric field is constant? I'm going to say no to both of those cases here. So if I look at what I have going on here with this cylinder here, is let me draw a few normals in here. The normal to the cylinder here are these purple arrows here. They're normal like that. So the normals don't look like they match the electric field very well in this region right here. I have no idea what that angle would be. The normal up here, everyone in the cap, might match this one electric field line that comes straight out of the point charge like that, okay. But even on this cap here, it certainly doesn't match this one or this one. So again, phi is a little hard to get there too. And over here, phi is impossible. And down here, this lower cap, the same issue happens there with phi. So I really failed to choose a proper phi there. And also, I can't really claim that at any point on this cylindrical surface is the electric field constant. I can't claim that the electric field all along, say, this edge of the cylinder is constant because it's sort of this far from the point charge up here, but it's really close to the point charge here, and this far from the point charge here. The electric field that I expect would be different magnitude all along this boundary here that I'm calling the cylinder. It's a poorly chosen Gaussian surface for this. And I'll sort of likewise say that if we drew another point charge over here, positive or negative, choose your pick like that, drew the electric field lines going out like that, if I put a box around this thing like this, I'm afraid I have the same problem now. The normals to the box look like this, these black lines. I shouldn't do them in black, let's do them in a purple color like that to delineate a bit. Here's the normals to the box right here. And if you look now, and there's a normal in the back there and so on, if you look now, the normals don't match up with the electric field lines at all here either. These electric field lines are going in all directions, and as say for one electric field line coming out that maybe it's going straight down like that and maybe straight up like that and straight out, only those 4 to 6 lines, there's ones coming out like that, all the others don't match. Like for instance, what is the angle between this electric field line and the normal right there? I have no idea. How about over here? Don't know. The other part that's bad about this is we can't claim the electric field is going to be constant everywhere along one of these surfaces here either, because like this surface, like the cylinder, is this far from the point charge, so the electric field will have a given magnitude, but it's a little bit farther from the point charge up here, so the electric field is going to have a different magnitude, because remember, for a point charge, the electric field is proportional to 1 over r squared. It matters how far you are away from the object. So of the 3 Gaussian surfaces, these 2 for the point charge just don't match the criteria that phi, or the angle between E and a normal to the area, is nice and predictable, and I just can't find a region on the Gaussian surface where the electric field is constant. So of course I know what you're thinking, why don't you just choose a sphere, and that would be the right answer, but that's exactly our point here. So here's the point charge right here, and you know for the point charge the electric field lines go out in all different directions like this, and they're all pointing outwards like that. We can draw little arrowheads on there. Like this, going in all directions like that. Now what we can do is the nice, most symmetrical surface I can put on is going to be a nice sphere now. So if I come in here and draw a circle going all the way around the point charge like that, let's look at what we have. So I'll just stick with the 2-dimensional drawing here, but realize that these electric field lines can come straight at you as well. Let's draw a few normals in here. This normal matches, that normal matches, that normal matches, that normal matches. All of these normals match up beautifully with any electric field direction you get. No matter what electric field is emanating from that point charge, there is a normal vector along this purple surface that matches it nicely. In other words, the phi in this case is all told 0 degrees all around. Every normal is parallel with every electric field line, and so you have a very nice, beautifully symmetric case. So you definitely met that first case there, that phi is going to be very easy to handle for you here. In fact, every one in the integral of the cosine of phi is just going to be 1, so you can just drop it out, and this left-hand side of Gauss's law is just going to become, you'll still have the circle around it here, just going to be E dot ds. So look, you've gotten rid of the whole cosine because the angle is so well behaved for the geometry that you've selected for that point charge in there. Now, what about getting this electric field to come out in front of the integral? We'll go back to your drawing here and look at it. Is the electric field at this point the same magnitude as the electric field at this point? I'm going to say yes to that because both of those points are the same distance from the point charge. How about here? Yes, here, yes, here, yes. All of these black points that I'm drawing around the circle are on my Gaussian surface and are the same distance from the point charge. So the electric field is nice and constant. So on this surface here, the electric field is not changing. So if I choose to integrate over this surface right here, E will be constant. So what that means is for this Gaussian surface, since E is just a constant relative to the surface, which is what that S stands for here, you can pull it out in front of the integral. So what you're left with then is E times the double integral of ds. Look how easy the left-hand side has become now. The angle's gone, the electric field is out front. The only thing you have left inside is the ds. So this step, absolutely, you always need to arrive at somehow during your process of Gauss's law, and it came from 2 facts. 1, phi was doable. I'll put that in quotes here. And I think doable first is always going to mean it's either going to be 0 degrees or 90 degrees. Or 180 or whatever multiples make the cosine either 0 or 1. But the point is that phi was doable. And number 2, we found areas on the Gaussian surface where the electric field was constant. These 2 facts here are what allow me to finally get the left-hand side, that's the only thing we're talking about here, the left-hand side of Gauss's law down to this simple formula right here. And so what we'll do now is well, sort of as a last step, what are you going to do with the double integral of ds? How can you sort of work that? What does it become here? Let's maybe go over to this side. what would you write now? Well, how would you process E ds? What would that be equal to? Well, if you just sort of translate it to English, that's probably the easiest thing to do. It says, hey, this is a surface integral here. Remember, two integrals mean a surface. The ring means it's a closed surface. So what this is really telling me here is that the area of the closed surface that I chose here. That's always what this is going to mean for Gauss's law here. The area of my closed surface. So that's one of the interesting things about this left-hand side of Gauss's law is there's never actually an integral to do. Because we'll just ask the question then, what is the area of the closed surface that led me to get this simple form of Gauss's law? It was a sphere. And what's the surface area of the sphere? 4 pi r squared. That's the surface area of a sphere. So you see, you're sort of done with this aspect of Gauss's law. Because now we know that the double integral of ds here is just 4 pi r squared, which is the area of a sphere. So you never actually have to do the integral. So all told, the left-hand side of Gauss's law, I realize I'm running out of space here, has just become E times 4 pi r squared. This is what the entire left-hand side has become. Not because of any mathematical tricks, not because of any strange formulas, but it's because of the way I systematically broke down this otherwise impenetrable form of Gauss's law. The double integral with a loop around of E dot ds became just E ds. Then I got my phi under control, so the double integral just became E ds. The cosine just dropped out. Then furthermore, for my Gaussian surface, I found how I could make the electric field constant, so I could pull it out in front of the integral. I'm just left with E ds, and then I could just translate this integral easily into English and say, well, what is this of? It's the area of my sphere, which is just 4 pi r squared. So this is what the left-hand side of Gauss's law has become. So what we've done now is you can actually write now in your formulas here that E, that 4 pi r squared, is equal to the enclosed charge over epsilon, and you're well on your way to using Gauss's law now. Now we're going to talk about this right-hand side in a different video altogether, but that's how the left-hand side would be processed. So before I leave then, we're just about to wrap this up. Let's just make sure we know what's going to happen here in Gauss's law. Just do a bit of a recap here for what you want to start with. You'll always start with a left-hand side that looks like this. But one way or the other, you always want to break it down so that dot product disappears. Either it's going to be 0 or give you a nice E dot ds. If it's 0, you don't have to worry about it because zeros don't contribute any to an answer right there. You want to get it down like this. Then you always want to get it down to being able to pull. If you chose the Gaussian surface properly, you'll have E is equal to constant. You can pull that out in front like that. And so what this side is always going to be here, depending on what you chose here, it's going to be the surface area of a sphere, which is 4 pi r squared. So this is of a sphere right here. If you chose the cylinder, it's going to be the surface area of a cylinder, which is something like pi r squared. Let's do it all in lowercase again. Pi r squared times L. So again, this is the sphere, surface area of a sphere. This is the surface area of a cylinder, not the volume now, but just the surface area here. So, in fact, I don't even think that's right. Let's just get that corrected here. The surface area of the cylinder, I meant to say, is something like 2 pi r L. There we go, that's better. If the cylinder has a radius r like that, this outer skin here that I'm coloring in purple here has a surface area of 2 pi r L. So sort of like the circumference around the circle once times L, which is the length of the thing here. And you might have to add, depending on how you're doing this here, the caps in here. This thing definitely have caps. So you definitely have to think about putting in a 2 pi r squared, something like that, because there's a pi r squared here and a pi r squared here. But I'm going to caution you, be very careful about this, because often you won't need either this or this. Very few times, if any, that I can think of, do you need both of them. Why? Because phi is definitely going to be 90 degrees for either this one or this one right here. In other words, you'll have electric fields that sure pierce the caps, but maybe at 90 degrees relative to the normal, so it knocks out, or pierces this other skin here, but at 90 degrees, so that it's going to drop out. But I'm just saying this is the full surface area of a cylinder with the caps in there, but you may not need all of the parts of it. And of course, the last one here is the surface area of a box. Now, boxes don't always have to be symmetrical like this, but in general here, they can have a length, a width, and a height like that or something. So now you sort of have to get the surface area of that. And just remember that what you have here, you have 2 of the front and the back, so you have 2 times an LH, something like that. That handles the front and the back right here. You have a twice width times height, that handles this and that side. Then, of course, you have a, looks like a length times a width, a 2 times LW here for the top and the bottom right here. So this would be the full surface area of a box here, but again, you probably don't always need all of these elements right here, because you have to look at, well, how is phi governing this side, or this side? In other words, you can have an electric field line that might be going through this side right here, but it might be at an angle that looks like this. So if the electric field is going up like that and the norm to the surface goes out, see there's a 90 degree in here. So you won't just always dump all these terms in here, but you have to be very careful to see, well, which one does the angular dependence of the phi cause to drop out or not. So in general here, these are the three cases that you're looking at here, and that's definitely how the left-hand side of Gauss's law would be processed. It's either going to be a sphere, a cylinder, or a box, but you have to be careful about looking how those electric field lines and the normals sort of sync up with each area, each portion of an area, in particular the caps, the skin, or what side's there of the cube.